Hello everyone, in this video we're going to talk about microscopic states and phase space. Consider we have a box, and in this box we have a bunch of molecules, and these molecules can move around in a random fashion in the box. They can collide with each other, and they can collide with the wall of the box, right? And we know that for a system like that, we can assign a bunch of numbers to describe the system. For example, we can assign the number of the particles in the box, and we know the volume of the box. And also, if we isolate the box from the rest of the universe, the system is going to have a fixed energy, okay, which is E, right? So knowing these numbers is sufficiently good for us to describe the system from a macroscopic point of view, right? But we know that even if we assign all these numbers, there's so many different ways that the atoms in the box can arrange themselves and then can have different velocities, right? So now we can take a snapshot, right? As the system is evolving, as the particles move around, let's say we just take a snapshot, okay? Which is basically illustrated as this box. So in this snapshot, what we can identify include the position of all the particles in the system, which we denoted by this vector x. And also, we know the velocity of all the particles in the box. So the collection of all the positions of the particles in the box and the collection of the velocities of all the particles in the box, these numbers defines it what we call a microscopic state. Now, why we call this a microscopic state? Well, consider that if you have all this information, right? You have this particular snapshot, and now you take the position of the particle at this particular time t, where you take the snapshot, and then you can advance the time a little bit, right? Because you know the velocity of each particle. For example, this is the particle 1 at time t, and because you know the velocity of this particle at time t, so you can advance the time a little bit, right? So this gives you a small displacement, and then what you can do is that you're gonna find out where is the particle at a later time, right? And you can do this also for the velocity, right? If you know the position of the particles, you know the force between them, and also you can find out the acceleration, then you can find out the change of the velocity, and then you can find a new velocity at a later time. So this means that once you know the snapshot of the system, which are specified by the collection of all the positions and all the velocities at a time t, in principle, you can basically evolve the system and then to recover the entire evolution dynamics of the system at later times. So that's why we call this a microscopic state, because it gives us a complete description of the dynamic state of the system. Now let's consider a specific example, for which we can write down the microscopic state in an explicit way. So this system is what we call the harmonic oscillator. It's a very simple system. You have a spring which is connected to a point mass, okay? And then let's say the spring constant is k, and the mass of this particle is m. We know initially if we give this thing an initial kick, it's gonna have a initial velocity, and then this guy starts to vibrate back and forth, right? So this is physically what's going on in the system. And we know that if you want to quantify, for example, the position of this particle, right? Let's say this is gonna give us the origin, and then our x-axis is in this direction, so this is the origin of the system. You know that it's gonna start from 0, and then it increase, and then when it reach the farthest point, where you have all of the kinetic energy converted to the potential energy, it starts going back, right? Passing through the same point, but in a different direction, and then it goes up, right? And then when it reaches up to the highest point, it stops and starts to move back again. So the system is going to keep on doing that. So you have this periodic motion of this oscillator, of this particle, right? So this is physically what's going on. Now, how can we describe the system? You know, we know exactly what's going on, right? But how can we describe this using the microscopic state? Now, remember what we have here is the position of the particle as a function of time. So this is what we have, right? But the microscopic state does not relate the position with time. It simply says that, okay, at any time point t, you should tell me where the particle is and what is the velocity of this particle. It's always a kind of different way of describing things, right? And you know that, okay, this is specified for every time point t, right? So you're going to have a bunch of those microscopic states as the system is moving. Okay, now how do we, visualize this, right? What is a convenient way for us to, to see these microscopic states? Well, to do that, right, we have to introduce a new concept we call phase space. Now, what is phase space? Well, a phase space is basically a very simple and illustrative way of seeing the microscopic states as time goes on, right? Now, let me explain this in a little bit more detail. So in this particular case, we know that we want to represent this microscopic state, right, in a diagram. So this microscopic state has two numbers, so our diagram should have two different axes, right? Now, one axis is going to represent the position of the particle, and the other axis is going to represent the velocity of the particle. Right? Very simple like that. Now, what we have to do is try to map this microscopic state to this graph, right? To this diagram. So let's get started, right? Initially, the particle is at the origin of the system, so we know that when t equals to 0, right, the position of the particle equals to 0 because that's where we said it's at the origin, and the velocity of the particle equals to v naught, right? It's a positive number. So now, how can we map this thing into the phase diagram? Well, let's just go to these two axes, and we find out, okay, this is when x equals 0 along this axis, and then let's find out this is when v equals to v naught. So this is going to be the first point, right? This is the first state of my system. And now we have to go back to the system and see what's going on if we look at a later time, right? Now suppose that we increase time a little bit, right? This is when t equals to t1. We know the particle physically, the particle going to move down a little bit, right? Corresponding to, increasing of the x value. But when the particle is moving down, right? So we're going to have some intermediate x which is greater than 0. But also we know that as the particle moves down, some part of the kinetic energy is converted to the potential energy, so the velocity can now get smaller, right? So this is what we know. So now we can schematically map this point also on the phase diagram, which will be somewhere here, right? So that now is the position going to be greater than 0, so it's going to be greater than 0 somewhere here, and the velocity going to be smaller than v naught, so it's going to be somewhere here, right? So as you can see that as the particle keep on moving down, the position can also keep on increasing, the velocity going to keep on decreasing. So maybe you're going to have another point right here, right? So the interesting thing is that when the particle stops, right? When the particle stops at this point, you know that it reached a maximum value for the x, right? But what is the associated velocity at this point? We know the velocity equals to 0 because the particle stops at this point, right? It reached the maximum, the lowest point, and all of the kinetic energy are now converted to the potential energy, so the particle stops. Okay, so that is basically this point. Okay, I think you already begin to see what the phase space can tell us about the microscopic state, right? And then we keep on doing this, right? As the particle passes the lowest point, get to the lowest point, it starts to, go back again, right? Once this thing goes back, it reaches here. So you can see that the x can now become smaller, but also the velocity become negative, right? And the particle is accelerating because at this stage, the potential energy stored in the spring is converted to the kinetic energy of the particle. So the particle is accelerating, but in a different direction. So as x gets smaller, the velocity is going to get larger, and then when the particle returns to the original position, right, it's going to reach a maximum velocity, but in the opposite direction. You're going to pass through this point in the opposite direction, right, and keep on going. Okay, when the particles start to goes up, I think the x, right, the displacement or the position now become a negative, but the velocity still become negative because still moving up, and it keep on doing that until it reach to the highest point. Okay, and then when it reaches to the highest point right here, it start to go back again, so the velocity become positive, and then you start to the displacement, the x, right, is still negative, but then the magnitude start to decreasing, so you can get something like that. Okay, So from this analysis, I think it's very apparent that, okay, now if we look at the phase space, right? We look at the space where we plot or represent the microscopic state of my system as a single point. As the system is moving in the real space or in the physical space, we also see a trajectory of the states, right? The microscopic state in the phase space. And in this particular case, the trajectory gonna looks like this, right? So we should connect that in this way. Okay, so it looks something like that. You may have, look at this. If you look at this, okay, it looks like something like a circle or an ellipse. But is this really a circle or an ellipse? The answer is yes. Now, why is that? Well, if you think about what this curve is about, right? This is about a connection or a functional relation between the velocity and then the position of the particle. Now, is there a functional relation between the velocity and the position of the particle? The answer is yes, right? So now if you look at the setting of the system, when we talk about this harmonic oscillator, we say the energy of this thing is conserved, right? There's no dissipation, there's no input of energy, the total energy is conserved, which means that if the system initially has an energy E naught, right, then this energy basically going to be, part of it going to come from the kinetic energy of the system with velocity v, and part of this going to come from the potential energy of the system, which is the potential energy of the spring. Okay, so now if you look at this, and then you can immediately recognize, okay, this is a equation for an ellipse. Okay. We can easily see that because you can rearrange these terms a little bit, right? If you don't see this is an equation for ellipse, we can write down this equation, rewrite this equation in this term. Okay, it's going to be 2 E naught divided by K, and plus this is velocity, 2 E naught divided by M equals 1. So you can call this your A square, you can call this your B square, and you can immediately see this corresponds to one of the semi-axes, this is another semi-axis, and then we have an equation for the ellipse, which means that this shape of the trajectory for the states in the phase space is an ellipse. Okay, so that's a very interesting result, right? So this is the insight that we get from the phase space analysis. Again, if we go back to the original system, we know this harmonic oscillator is moving back and forth, and this is the picture you have. If you plot the position of that harmonic oscillator, that particle as a function of time. But now if you use a phase space picture, instead of looking at the relation between the position and time, we look at what is the relation between the position and velocity at different time. And then we map all of these microscopic states onto this particular phase space. We'll see that as the system evolves, the trajectory, the phase space, the states in the phase space also form a trajectory. And we know exactly what is this particular shape of that trajectory. That is the phase space of this harmonic oscillator. Now let's take that insight back to our original system, this NVE system where we have a box containing particles, right? How this system is connected to the harmonic oscillator. Well, of course, it's quite different to the harmonic oscillator in many different ways, but one similarity between the two systems is that the harmonic oscillator has a fixed energy, and then this box also has a fixed energy, right? So this means that, well, although it's much more complicated, but there is an energy conservation equation, which basically it means that, the total kinetic energy of the system, which is the sum of the kinetic energy for each of the particles, right? And then plus the total potential energy of the system, which depend on the position of all the particles, equals to a constant. That's basically what we can say about this box, right? So this means that if we want to do a similar thing as we did for the microscopic state for the harmonic oscillator, if we want to use a phase space to visualize or to imagine the trajectory of all these particles as they evolve, right? Now the phase space should look similar to the harmonic oscillator. Now in particular, okay, let's set up the phase space in a highly schematic way. Well, because for now, we still need one X to represent every single number in here, right? In here, we have so many different numbers because each position now is a vector. Now, if we talk about 3 dimensions, now each position needs 3 number, and each velocity also needs 3 number, right? And then we have n different positions because for each particle we have a position vector. So we have n different particles, we have n different position vectors. So this means that the total number you need, right, to define all the positions of all the particles in the system is 3 times n. And following the same argument, the total number you need to define the velocity of all the particles is also 3 times n, right? Now we know that for each number, you will need an axis, right, in the phase space. So the phase space for this guy is a very, very high dimensional object, which there's no hope for us to really show that in a rigorous way. But so what we did is just to show this in a very schematic way, right? So I will just use this single axis to represent the collection of all of the positions, and then we'll use this axis to represent the collection of all the velocities, right? So now in this case, now what we want to do is that given there is an energy conservation equation, so if you were able to, for example, very schematically map the microscopic state into the phase space, you can get something similar to what we did for the harmonic oscillator, right? Because there's one equation connecting all these numbers together, this means that in the phase space, there has to be a closed surface, right? All of the microscopic state has to fall onto a closed surface. And when the particle is evolving, you're basically visiting these different microscopic states in a particular sequence, okay? And eventually, this is going to form a closed loop because your total energy is conserved, okay? So that is the insight we get for the microscopic state, and then about phase space.